So last time we learned how to do PCA. We'll continue with that today and make sure you all have learned how to do PCA and you can produce a plot. And then we can continue with discussing phylogenetics a little bit. Okay. I'll give you an overview of PCA, and then if you have a question, let me know. So, we discussed PCA, and if you look up PCA in Wikipedia, you'll get a definition like this, which is kind of difficult to understand, but what matters is this word, this phrase, dimensionality reduction. So you're trying to reduce the number of the dimensions in your data. In phenotypic data that we have, each phenotype is a dimension or a variable. So if you have 100 phenotypes, then you have 100 dimensions. And in SNP data, we have the one that we use for PCA has 10 million SNPs in it. So there are 10 million dimensions. And there is no way we can plot that visually. So PCA will help us reduce the dimensions into one or two. And that's what dimensionality reduction means. For us, we use PCA for two reasons. One, just to see how diverse different groups are. In the PCA plot, when the dots are far away from one another, that means that they're very different. So they have a higher genetic difference. But if they're very close to each other, that means they're closely related, or they have lower genetic distance. And based on that, you can kind of get an idea about the diversity within each group. So if those dots are very close to each other, then diversity is lower among them. So the other purpose that you can use PCA for is to cluster. So in machine learning, one approach that is used for clustering things is PCA. So, for example, if you have, if you're trying to write an algorithm that can detect tumorous cells from healthy cells, then you can use PCA based on, let's say, genetic data or expression data, and PCA can quickly summarize the results and then tell you whether it belongs to the tumorous group or healthy group. So there are different ways that PCA can be used, but that was just one example. So in simpler terms, if we have a data set with so many variables, we can reduce the dimensions into just one or two, and then explore the data in simpler plots. So we did PCA last time. I'll give you a quick overview of the code we used. So we have two packages, one called GDS-FMT, which is short for GDS format. This is a package that can turn our SNP data into a simpler format that we can use in R. And SNP relate is a package that can do PCA on large data. PCA, it's embedded in R. Without any sort of packages, you can do PCA. But SNP relate is a package that's specifically designed for working with SNPs and doing PCA and so many other kind of analyses on SNP data. Then we add the population data, which it showed us what each population looks like, what accessions we have in each populations. And then I explained these BIM, BED, FAM files. These are all from a software called Plink. And in Plink, you can convert your VCF file, which has the variant information, into Plink format, which comes in 3 shapes: bed, FAM, and BIM. The FAM is just the list of accessions, and sometimes you can add phenotypes to it if you're doing GWAS. But the other two have the list of SNPs as well as the genotypes. Then there is the command called snip GDS bed to GDS. So this is a function that can turn your bed file, which are these Plink files, into a GDS file. And for that, you have to tell, you have to define the bed file, the FAM file, and the BIM file, which we did up here. So what this does is takes these 3 files and converts them into a GDS file. And then snip GDS open is a function that opens that file and saves it into a file we call geno file, or that could be short for genotype file. So all the genotypes will be there. Then we extracted the SNP IDs and the sample IDs. For us, these are all the accessions as well as the PI accessions. And then SNP GDS PCA is the function that does principal component analysis using the geno file. Then we define the SNP ID. And we say autosome only false. If you remember, I said that originally these packages were made for human genome, and in human genome you have the sex chromosomes and autosomes. So autosomal chromosomes. So if you wanna just do the PCA on autosomes, then you would say autosome only is true. But for us, we don't have that separation in our chromosomes, so we want to use PCA on all chromosomes. That's why we say autosome only equals false. Remove mono SNP. This is the case where the SNP is only in one individual. We can say true to this or false. Our data set has already been filtered for removing SNPs that are present in only one individual. So we don't care about this option much because we already have done it. You can do false or true and it won't affect the results. And this is the number of CPUs. I use 64 because we ran this on the cluster, and on the cluster we have a lot of CPUs available. On a personal computer, this can be maybe 4 to 8, depending on how good your computer is. But I wouldn't recommend doing this analysis on a personal computer. These kind of, like when you have like 10 million SNPs and things like that, when you get into the range of gigabytes and gigabase pairs, then you shouldn't be using your personal computer. Any questions so far? All good? Okay. So, let's see if we can add you all to the cluster so that we can run some analyses. So I'm gonna go to my reservation. and add everybody to the cluster. Paul, did I add you?
Oh, pardon.
What's your kernel ID?
Oh, PC644.
Okay, I've already added you. So you all can go ahead and connect to the cluster with CBSU LM10. The way to connect is with terminal. So I'll get out of here real quick so that I can show you. So in the terminal, you would type CBSU LM10.biohpc.cornell. So this is going to be SSH, then your ID at CBSU LM10.biohpc.edu, and then you type your password. If you have any problem, let me know.
I'm still trying to log in. I just forgot my password, so I'll get it pretty soon.
Okay. Okay. Did you all have a chance to install FileZilla? Okay, you can do it now. It shouldn't take too long. I'll pause the recording and we'll install the software that we need, and then we'll come back.
Where do you go to install it?
So FileZilla, there's some instruction on the when you sign up for an account on BioHPC, it gives you information. So let's see here: user guide, quick start guide, get an account, lab credit, transfer data, step-by-step summary for how to transfer data. One is FileZilla. So it's called this address that I'll put in the chat. Okay. So you can go to this link and then quick download links, download files of the client. And then for the Mac version, you would download this. Windows people have to download the Windows version for themselves. And then I'm not going to continue this because I've already done this, but if you click, it will download and install. After you download and install, then we come back here and I'll explain how you can connect to the server. And we'll pause the recording for a second. When you go to FileZilla, when you open it for the first time, this site might be empty. But what you need to do is click on this icon at the corner and then left click on new site and then change the protocol to SFTP. And the host will be cbsu lm10.biohpc.cornell.edu. Then you type username and password and connect. Here you can click on the name where it says new site. Instead of new site, you can copy paste this part of the name. CBSU LM10. This is the name of one of the computers on the cluster that we can use. So you save it, and then you don't have to remember this in the future. You can just quickly log in. So one more time, you click on new site, then you change the protocol to SFTP, then you type in the address for the computer you're trying to connect, then you type your user ID here and password, and then you can change the name from new site to something more like this, and then hit connect. Try that and let me know if that works. To access the work directory, you need to type /local/workdir in the remote site. And let me know if that works for you. Okay, so you're supposed to see HR 355 and root. So /local/workdir, and this is what you're supposed to see. Paul, did that work?
Yep, it works for me.
Cool. So you can, here you can make directories for yourself. So you can call it after your name. You can call it, I'm going to call it Hamid, but you guys can call it your own names. So you make a folder. It's the same thing as mkdir that we do in terminal. So it does the same thing like mkdir that you did, like make directory Hamid. So, and so I see Paul's folder. But I don't see Eddie's and Diego's. Do you guys have issues? Do you guys have any trouble?
Are you trying to find our workspace?
So did you try making a directory for yourself?
Right now?
Yes.
Not yet, not yet. Sorry. We're figuring out
Eddie
how
was
to.
helping me out with one thing real quick.
No problem. So I'm going to copy this file called all variants xmath2p.gds into the current directory. That's the snip file that has, it had about 10 million sites. Then I removed the SNPs with minimum allele frequency below 2% from it. So if you type ls, now you're going to see this file. And I believe there is a way for me to allow you to use this file, because I have to give you the sharing. I keep forgetting how to do that. Try copying it and see if it works. So you need to copy this into your directory by saying cp, name of the file, and something like this.
Yeah, it says permission denied.
Okay, let me quickly remember file permissions, Linux. All permissions for to send. Richmond. 755. See if it works now. It did? Cool. Okay. Did it work for you, Paul?
I'm still copying.
Okay. Make sure you copy it to your own respective folders. Don't copy it into my folder. Okay. Now I don't have permission to see your folders.
Okay, it's in my folder.
Okay. That's fine. As long as you see it there, then it should work. So now we change directory into our own directories. So I'm going to type cd Hamid, but for you guys, it's going to be your own name. And there I have to see this file, this GDS file. Do you all see it? When you type ls, do you see that GDS file?
Yep.
Okay, now if you just type capital R, it should open up R, and it gives you a welcome message. Here it tells you the version of R. The last update was a few months ago. They call funny names to each version of R. I think they come, each version comes out every 6 months. So, and we have to load a few packages. The packages that I talked about, the GDS format and snip relate. So we have to load those. I'll put that in the chat. So library is a function that loads a certain package. So we write two library commands here, one to load the GDS format package and one to load snip relate. And after you load, you should see this message at the bottom. That means that it's all good. Good. Cool.
Yep.
Great. Awesome. So the other file that we previously used is called populations.csv. I forgot to tell you to copy that, but we can do that now. We can get out of R real quick by typing Control D. And it says save work space image. You say no by typing N. Get out of R. Then we should copy that. Go back one cd dot dot. Go back to working directory where the folders are, and I should copy the. So let's see, yeah, the population file interview CS3 into here. And give you permission to copy it. And then you copy that population file into your directory. So in your directory, when you type ls, you should see two files. One is the SNP file and one is the population file. Did it work for Eddie and Diego? Okay. Let's start R again and load the packages by the library commands. And then this time, if you type populations, read.csv and then the name of the CSV file, it should be able to load the population. So I'll put this in the chat. And I'm going to go ahead a little bit more quickly because we covered some of these in the last session. So to save time, I'm going to go a little faster, but feel free to pause and ask questions. So, and then because we have already done these steps, we have converted our print files into GDS file. We can just use this command. We can skip these and just use this to open that GDS file. Put the command in the chat. Snip GDS open and the name of the file. Then we have to find the SNP IDs and the sample IDs. So the last two commands take the genome file and take this genome file and read the SNP ID from the genome file. And after you do those, we finally get to do PCA. The total number of CPUs on the cluster is 64, but there are now 4 of us using it. So I'll reduce this to 12, or 64 divided by, so 32, 16 maybe. And if you do this, it will start running PCA. So to explain this command, snip GDS PCA means that it runs PCA on snip GDS file. And I explained what autosome only means and remove one's mono snip. So you can just run this command that I put in the chat. And then wait. It should take about a minute for this to finish. Let me know if you have any questions. It's finished for me. Let me know when it works for, when it finishes for you.
Oh, Hamid, how come like 4 of us running the same thing on the same CPUs doesn't slow it down so much?
We are, so here there are 64 CPUs and each of us are using 16 of them.
Oh, okay.
So I changed the number of thread, which is the number of CPUs, to 16. Did it work for you all?
Yep.
Cool. Diego, all set? Cool. Okay, now we have a file named PCA. If you type head parentheses PCA, you should be able to see it. So it's a big file. And what's interesting is in it is these eigenvectors, which are the reduced. So these are the axes that our data is reduced into. And eigenvector or PC or people call it principal component or eigenvector. And these are the kind of like the summary of the data. And usually or always the first eigenvector or the first PC is the one that has the most variation in it. And then variation reduces to the second and so on. And people usually plot the first principal component and second principal component. So that's where that is. You can type this head PCA $ eigenvect, and this is going to show you the principal components. It's showing that we have 32 principal components, and we can also calculate how much of the variation each principal component represents. So we can type these two. The first one calculates it, and the second one shows us what are the top principal components. And in the second command, there's the round option, which rounds the percentage to 2 decimal points after, two digits after decimal points. What this says is that the first principal component, the first axis up here, this one, explains 23% of the variation. In other words, that's kind of like saying we have summarized 23% of SNPs into just one axis. And then the second one is represents 12%. And then the numbers keep going down after that. So if we plot first axis and the second axis, we are capturing about 36% of the variation, which could be good enough for just visualization and clustering. Then the next line of code is to make a data frame where we have the accession numbers as well as the EV1, which is the first principal component, and EV2, which is the second principal component, and so on. So we're saving multiple of these. This is just for reference. We're doing this so that we can use it in the future. And tab here is short for table. So we're creating a table that has all of those principal components in it. So we're keeping the top 5. And then we also add the accession names to it. Let me know when you see this on your screen. Are you all set? Good. Cool.
Still seems to be running. Is something supposed to pop up?
Yes. Can you share your screen?
This?
Okay. Hit enter. Oh, there is a problem with the code. when you copy paste it. Looks
Okay.
like didn't. Just type tab for now, real quick.
TAB or press tab?
Yeah, TAB.
Oh.
Okay,
Okay.
so that worked. Only the last command that you copied seems to be relevant. Try it again.
Yes.
Okay.
Hmm.
Wait. So it looks like it worked. So when you type tab, or you can type head parentheses tab. Yeah, looks good.
Okay.
So now we get to actually plot, which is exciting. But before we do that, we have to add the IDs. Here our table has only the accession names, but we want to also have the IDs saying which one is Ovigerum, which one is Melongena, and which one is Insana. And that's where that kind of information comes from this population file that we previously loaded. If you want to make sure it's still there, you just type populations here and hit enter. So it should show you this information with accession, population, and ID. We haven't defined any populations yet, but the major group IDs are there. So you have to be able to see that, and to test, quickly just type populations and hit enter and tell me whether you see that. All set?
Yep, all set.
Oh, Diego, did you see
Yeah.
the part? Okay.
I think I'm missing
Oh.
the populations file. Even I thought I was able to copy it into my directory, and I guess
Oh.
I shouldn't leave the R session, right?
If you leave, then you have to come back to it. But we're almost there. So
Probably look on from Eddie's script here. He has it open.
okay, no problem. Then you can repeat all of these later, and by just copy the file into your folder and repeat all of these. We're almost at the end of this, so you don't have to redo all of this.
Sounds good.
Yeah, so we're gonna merge the table that we just created with the population. What this is gonna do is to add the accessions. Sorry, it's gonna add, we already did that, sorry, I forgot. So I'll repeat this to double check. Now we have a table with the IDs. And then I'm gonna get rid of the population folder. I'm getting rid of the population column. So in the tab, there is a population column that doesn't have anything in it, it's all NAs. So I want to get rid of that. And to do that, you just say tab $population equals null. And then you write the table tab and give it a name, PC output. What this is doing is saving the table that we just created. Put this in the chat. Here's the chat, okay. It's a good idea always to save the output into an actual file. So in case something happens, you have a copy. Now, if you go to FileZilla, you should be able to see under your directory, you should be able to see this. You should be able to see this file that says PCA output.txt. And if you right click on it, you can download that. So you can download this to somewhere on your desktop, on your computer. So if I download this now and open it, let's see where it went. Let's see. Okay. This is just a text file with this kind of information, just the accession numbers as well as the
Directory? You think
principal components.
Yeah.
Think I could what?
Take your file from here and throw it inside the work directory.
I might be able to, yeah. The PCA one?
Yeah.
Yeah, why is it not showing?
So, Diego, one way to overcome the issue you have is to copy that file, like you said, copy it into your directory, the population file from FileZilla. You could just drag and drop like this.
Yeah, that's weird. It's in there.
Yeah, I'm not seeing the PCA thing in my folder.
Okay. Okay, let's see your screen.
I'll just share my whole desktop. Let's see. I just
Okay,
ran.
so, okay.
Sorry.
So I see populations, CSV, no, that's, let me see you. That looks right. So try again. Maybe you need to refresh.
Oh, Hamid, I'm also getting the error. I think it's
What?
yeah. I'm also getting the error. Permission denied.
Oh, wait a second. Well, try opening your folder. There's an issue. Will you, Eddie, at the top, there's a refresh button with those green and blue arrows. Yeah, try that. There we go.
Oh, there it is.
Okay. That works. Let's look at Paul's screen. Will you share your screen? Okay, looks like it works. Those past errors, you can ignore those. So looks like you got disconnected for some reason. And try connecting again with the site manager. Say okay. Or you can do abort, please. There you go. At the top remote site, you type /local/workdir. There we go. All good. So one thing I want to point out is that the left-hand side of FileZilla is your computer. So you can find a place there and make a folder for your analyses. And you can download the output from today there. We're going to also download the final plot that we make. So I'll explain that in a second. We have to define colors and symbols for all of them. The symbol is symbol number 1. Let me share that real quick. So the symbol is here, tab dollar symbol equals 1. And color is gonna be 0 because we're gonna just change these. Let me give you the code real quick. So tab dollar color equals 0 and tab dollar symbol equals 1. We're gonna keep the symbol the same for all of them, but we're gonna change the color depending on the type of identification they have. So for Lasicarpon, we're gonna use gray. For Insanum, we're gonna use green. For Ovigeum, we're gonna use yellow. And for Melongena, we're gonna use purple. Okay. And then here's the part where we get rid of NAs if the ID is NA. So if the accession, one of the accession doesn't have an ID, we just don't include it. And then we write a for loop to color each group. So here it says tab, where tab ID equals population names I. The first one will be Lasicarpon. So all cases where the population name equals Lasicarpon, we will color it by the first color, which is gray. So pop colors we defined here, pop names equal here. So what this for loop does is matches all of the population names with a certain color. So give you these. And finally, we get to draw our plot. So you just give it a name. I'm calling it PCA 2 and 1. So because I'm plotting the second and first axes, tab $EV2, which is the x-axis, and tab $EV1, which is the y-axis. And then xlab means the label of the x-axis, which is PC2. ylab is the label of the y-axis. And then we define the colors, and then define the symbol, which is the same for all of them. And do you want to put a frame around the plot? Previously, I said no, but I decided that it's a good idea to have that. And alias, I think, is the font. And if you want to have a legend, you can do that. Here you say top left, meaning where you want to put the legend, and color will be population colors that we have defined. So you can just run this. And let's see what we have here. Okay, I won't open it until you all have it.
Hamid, I haven't ever. It says replacement has 1 row, data has 0.
Let's see your screen.
Wait, sorry. Share screen.
So tab is not okay. So pop name has been defined. Okay. You can maybe repeat the codes from, let me see, just quickly. I'm not seeing the chat anymore. Do you see, can you show me the, open the chat? Okay, no, I got it, sorry.
Okay.
Anyways, so from where we defined, so all the codes that we wrote after write.table, yeah. So tab $colors. So I'll show you which ones. If you could repeat these all the way to here. So tab $color symbol, pop names, pop colors, and then getting rid of the NAs and then defining the colors in the folder.
Okay. Oh, I don't think there was a getting rid of NAs. Oh wait,
I
there
think
is.
that, yeah, you wrote it, I saw.
Wait. Okay, the error comes up. The error comes up when I do the tab.
Okay.
The tab $color equals 0.
Okay, let's, I think your tab might be the problem. Keep sharing your screen. Share your screen one more time. Okay, type tab, just tab. Okay, something happened to your tab. We have to remake that tab by this command. So you would redo all of these, starting from data frame.
Okay.
At each step, you can type tab to make sure it's still there.
Yep. Okay, still there.
What step are you in?
Oh, then now after I type the tab equals NA, then it gives the error again.
Okay, so I don't know.
So it seems to be the tab dollar
Okay, is there a
colors.
way I can? Is there a way I can see your screen when you type them? Okay. So you can just bring back the passcodes onto the data frame. So you just press the up arrow, bring back the data frame one. Okay. Now, hit enter. Okay. Then write the merge one with tab and populations. So, okay, maybe you should stop sharing and I'll show you the script. Okay, so what's happening is when you copy paste, some of these have line breaks and that might cause issues. So you can just type this tab, merge tab populations by accession. And oh, did we lose Paul? Shoot, looks like we lost Paul. Okay, Diego, and did it work for you guys? Do you see the PDF?
Yep. I changed the legend so it was in the top right because it was
Okay.
blocking.
Cool. Can you open it?
Do you want me to
Yeah,
share?
sure.
Eddie's becoming a wizard in R.
Nah,
He's already a wizard.
nah, not yet. Said all that and I can't even open the PDF.
Leave it on the computer. Leave it on the computer.
What's going on? Oh, there we go. Okay.
Nice. Very cool. Great. So we accomplished what we were trying to accomplish. You got the PCA plot. And in the next session, we'll discuss how to use the same sort of data and the same package to make a phylogeny.
Okay.
I'll pause the recording.